All right. Let's keep talking about number theory, shall we? So I think on Friday I have a volunteer for presentation. I think this chapter is on Leonard Euler, right? So Trey, it was your group that's going to present on Friday, yeah, on Leonard Euler. Again, I don't know. I hope that it's clear to you who I think are probably the more impressive mathematicians of the historical landscape. I would say that one, for sure, is Archimedes. I think that Euler is right up there as well, though. What Euler did and the position that he put us in as a mathematical community is pretty impressive, to say the least. Okay, so we'll see a little bit about that on Friday. And actually, Euler was a good guy. He was loved by many. That is not something that can be said about a lot of other mathematicians. A lot of them were pretty self-seeking. A lot of them were pretty, hostile at times, discouraging to others. A mathematician of that ilk would be someone like C.F. Gauss. Gauss was sort of known as being pretty hostile. That was not the case with Euler. He was a good guy, for sure. Hopefully that will come through in the chapter. Okay, so let's keep talking about number theory. Now remember, let me just kind of remind you of a couple of things. This mod stuff, this mod notation comes from the division algorithm, right? So we take an integer a, we divide by a positive integer d, and we discussed why it's possible to restrict our attention to positive divisors. And we see how many times d goes into a. That will basically be the quotient, but things get a little weird if we end up with a negative number that we're dividing into. Remember that? We ended up maybe going in one additional time than we had anticipated. Okay, so I can see the quotient and the remainder is always between 0. Well, it could be 0 if you have perfect divisibility, but it's never more than the divisor, and that makes perfect sense, right? It makes perfect sense that it would never be more than the divisor, because if it was bigger than the divisor, then you did not go in enough times. But there's this notation that we use, a div d, that's the quotient. I talked about, like in the C++ programming language, how oftentimes, or there's actually an operator, like the division operator, that gives you that. R equal to a mod d, that's the remainder, okay? So when we're doing this remainder arithmetic, we were kind of going through what sorts of things are true. So suppose a mod m is the same as b mod m. Basically, that means that a and b both have the same remainder upon division by m. Yeah, that's what a mod m means, or these things being equal, that's what that means. Same thing with c and d. C and d have the same remainder upon division by m. Then this is basically saying that when I add a and c together, then it's the same thing as adding b and d and taking that mod m. Yeah, I'm going to get the same thing. Same thing with multiplication. And if a and b are the same mod m, then a minus b, what did we talk about? What happens to the remainder if I subtract those two things? Cancels. And what's left is something that is perfectly divisible by m. Okay, so that is a minus b mod m is 0. That means the remainder is 0, which means that m perfectly divides the difference between a and b. Okay, very important. A mod m equal b mod m if and only if a minus b mod m is 0, if and only if m divides a minus b. Here's this little example at the bottom. 13 mod 3 is the same as 7 mod 3, right? What's the remainder of 13 upon division by 3? 1. What's the remainder of 7 upon division by 3? 1. Okay, so those two remainders are the same. And notice that if I take 13 minus 7, I get 6. which is perfectly divisible by 3, right? So 13 minus 7 mod 3, that's 0. So, and that is the same thing as 3 dividing that difference, okay? Okay, we're just trying to live in this clock arithmetic realm and figure out what it looks like to live in this realm, okay? What it means to add and multiply, etc. Okay? Now, let's talk a little bit about how to do algebra in this realm, okay? Additive inverses. So given an integer a, what is an additive inverse of a modulo m? What I mean by that is, can you think of an integer x such that a plus x mod m is 0? Okay? Well, it turns out that x equal to m minus a will work. So for instance, let me just kind of convince you of that with an example. So let's see, let's do, so first of all, 5 mod 7, okay? Can you think of something, so by the way, 5 mod 7, what is that? Just, you know, so we're not horsing around here. What's 5 mod 7? It's just 5, yeah? If I divide 5 by 7, the remainder is just 5, okay? So watch this. What I'm saying here is if I take, so can you think of something such that if I add it to 5 and take it mod 7, I end up with 0. Can you think of something that would work? How about 2? Yeah? So indeed, 5 plus 2 mod 7 is 0. And notice that 2 is equal to 7 minus 5. That makes sense? Which is what we're saying right here. If I take the modulus minus a, it will work. But there's weirder things that I can do here. So for instance, let me go up here to the top. So like 9 mod 7, of course, what's 9 mod 7? 2. That's the remainder upon division by 7, okay? Can you think of something such that 9 plus x mod 7 is 0? This would be an additive inverse, yes? Of course, if we were working in ordinary numbers, 9 plus x equals 0, you would all immediately say -9, obviously, yeah? You would know exactly what to do. So what's the answer in this case? Well, yeah, there are several options. 5 would work, yeah? You guys see that there's not just one option? 5 would work because 9 plus 5 mod 7 is 0, yeah? -2 would also work, yeah? There are actually infinitely many things that would actually work here, yeah? So the algebra gets a little weird in that sense. But for sure, let me just say, for sure x equal to the modulus minus 9, which is -2, works. Okay, but so does, you guys already said, so does x equal to 5, right? That would also work. And lots of other things, even x equal to 12 would work, wouldn't it, right? 12 plus 9 is 21. If I take that mod 7, I get 0, yeah? So there are lots of options.
So 0 is just the remainder?
Yeah, that's right. I mean, when you're doing modular arithmetic, it's always, you're talking about the remainder, yeah? So you're kind of going around the clock and you're figuring out what the remainder is, okay? Any questions on that? Okay. What about multiplicative inverses? Multiplicative inverses. Now, an additive inverse, you know, is a number such that x plus whatever you're at gets me back to 0. We just talked about that. What about a multiplicative inverse? Well, they actually don't always exist. Remember, what realm are we living in here? Integers. Okay, so for instance, if I have like 2 and I want a multiplicative inverse for 2, it's no fair saying that it's 1/2. Do you know what I mean? 1/2 is a fraction, not an integer. Okay? So we have to be careful about multiplicative inverses. For instance, is there anything such that 2x, okay, so that is, I'm taking 2 times x, and I take this mod 6, is there anything that gives me 1? Well, I could try lots of things. I don't know, let's see. Does x equal to 0 work? No, that's really stupid, right? I mean, 2 times 0 is 0, right? And if I take that mod 6, I'm going to get 0, not 1. Yeah? What about x equal to 1? Does that work? No. 2 times 1 is 2. I take that mod 6, I get 2, not 1. What about 2? What about x equal to 2? Does that work? No, that would give me 4, which is not what I want. Okay, what about x equal to 3? Does that work? No, 2 times 3 mod 6 is 0, which is weird all by itself. Do you know what I mean? I just took 2 non-zero things and multiplied them and got 0. Okay, that's not something that happens typically with real numbers, right? If I multiply 2 non-zero things, I don't ever get 0. But when I'm working modulo something, it's possible to get 0. Okay, so that definitely doesn't work. What about x equal to 4? What's that give me? 2 times 4 mod 6 is 2, which is not 1. That's not, that doesn't work. That doesn't work. Okay. Okay, what about x equal to 5? Nope. That will give me 4. Do I have to keep going forever? No, because everything else, look, I just went through 0 through 5. If I went to 6, for instance, that's really the same as what? If I'm working mod 6, 6 is the same as 0. Just like 12 would be the same as 0. And -6 would be the same as 0, yes? Going through these kind of basic 0 through 5 covers everything. Everything else that I try to plug in here is going to behave the same, right, as one of these. Okay? So there is no multiplicative inverse of 2 modulo 6. Make sense? There's no multiplicative inverse. There's nothing that we can multiply 2 by that will give me 1. Yeah. Well, yeah, that is a form of, right. So if you're on the unit circle, you kind of wrap back to the beginning. I mean, that is a form of modular mathematics. Yes. Yes. That's a good point. Right. These periodic functions do that. They start repeating after a while. Okay. Other questions? What about, let's see. What about 5? Does 5 have an inverse modulo 6? Is there something I can multiply 5 by to give me 1? Does 1 work? No. Does 0 work? No. Does 2 work? 5 times 2 is 10. Mod 6 is 4. No. Okay. 3? No. 3 times 5 is 15. Modulo 6 is 3. 4? Nope. That's going to be 20 mod 6 is 4. 5. Yes. Okay. So x equal to 5 works. And by the way, so will anything that is the same as 5 mod 6. Yeah. And by the way, sometimes this is kind of weird, but you use a geometric term oftentimes when we talk about things that are the same modulo something. You say that those numbers are congruent modulo 6. So for instance, like 5 and 11 are congruent modulo 6 because they have the same remainder upon division by 6. Okay. So there's a notion of congruence of integers when we're doing this modular arithmetic stuff. Okay? X equal to 5 works. 5 times 5 is 25. I take that mod 6, I get 1. It's kind of weird, right? So 5 has an inverse mod 6. Okay, so what should be a question that immediately springs to mind about these inverses? So, you know, sometimes they exist, sometimes they don't. So what's the question? When do they exist? Like, under what conditions do I know that an inverse is going to exist? Yeah, that might seem like a useful thing. And by the way, I mean, it seems fairly clear that this would be a needful thing to know if you're going to do algebra in this modular realm. You need to have additive inverses, and we already saw that we do. But it's also nice to have multiplicative inverses. When you solve algebraic equations, don't you need multiplicative inverses? Yeah. If I say 2x is equal to 5, you immediately go, oh, just multiply it by 1/2 and solve for x. Yeah. Now, we need a similar thing when we're working in this realm. We need multiplicative inverses to solve algebraic equations. Okay. So inverse of A modulo M. Okay, an inverse of A modulo M is an integer, and we use this notation A bar on purpose. We don't put, well, at least I'm not doing it now. It's confusing to use A to the -1 because what's that going to make you think of? So notice I'm not using A to the -1 as the notation. Why would that be confusing for me to use that notation? Yeah, right. So you might think, oh, it's 1/8. No. Okay. So we use A bar as our inverse notation. Okay. And inverse of A modulo M is an integer A bar such that A bar times A mod M is 1. Okay. What does that mean? Okay, so for instance, we just did this one, 5x mod m equals 1, or let me just say 5. Let me rewrite that. So what I'm saying is 5 times 5 bar mod m is 1. And what did we find out that 5 bar was? What is the inverse of 5? 5 bar is what? What did we discover? 5 bar was actually 5. Okay, that was kind of weird. Okay. So what does it mean for like an inverse to exist? So A bar A has a remainder of 1 when I divide it by M. Yes? Okay. So what that means is that A bar A, okay, this number is equal to some multiple of M. So it's K times M plus 1. There's a remainder of 1, yes? What I'm doing here is I'm thinking of A equals QD plus R, yeah? So in essence, we've divided A bar A by M, okay? K is kind of like our quotient, yeah? And you have plus 1 as the remainder, okay? So look, here's a little example. A bar is 4 is an inverse for 2 modulo 7. What's 2 times 4 modulo 7? 1, right? So that means 4 is an inverse for 2 modulo 7. Okay, and apparently that means we should be able to write 4 times 2 as 7 times something plus 1. And we can, yeah? It's 7 times 1 plus 1, okay? Now remember, we said that 5 times 5 mod 6 is equal to 1, right? So apparently I should be able to say that 5 times 5 is equal to 6 times something plus 1, right? Because if I divide by 6, I should have a remainder of 1. So 6 times what plus 1 works? 4, yeah? That would be like the quotient. So anytime I have two numbers that are inverses, modulo something, I should be able to write that product of those two numbers as The modulus times something plus 1. Okay? All right, any questions on that? We still have this open question as to whether an inverse exists, right? And we need to kind of sort that out. Are there any questions on this? Okay. Moving on. Here it is. When does an inverse exist? Okay. Two integers, A and B, are relatively prime. That doesn't mean they are prime necessarily, but they're relatively prime to each other when GCD of A and B is 1. What is GCD? Greatest common divisor. That means they have no common divisors. Yeah? So relatively prime means that these two numbers have no common divisors or no common factors. They have nothing in common. Yeah? In terms of divisors. And we'll kind of talk about that, the notion of greatest common divisor at length here in just a minute. But does relatively prime, I mean, does that notion make sense? It just means they don't have anything in common. So what about two even numbers? Are those relatively prime? Absolutely not. Because what do two even numbers always have in common? 2. They have that as a common divisor. Yeah. Greatest common divisor being 1 means really the only divisor of both is 1. Yeah? Let me ask you a question. What about 5 and 6? What's their greatest common divisor? 1. They're relatively prime. Yeah? What about 2 and 6? What's their greatest common divisor? 2. What about 4 and 6? What's their greatest common divisor? 2. What about 3 and 6? 3. 1 and 6? 1. Notice that nothing else, right? There wasn't anything like 2, 3, 4. None of those had inverses modulo 6. Yeah? Multiplicative inverses. But 5 did. And it's because 5 is relatively prime to 6 that it has an inverse. And that's in essence what this little theorem says right here. If A and M are relatively prime, so A is the number we're working with, M is the modulus, right? So M, I keep using M for the modulus so you remember what role that's playing. If A and M are relatively prime integers and M is bigger than 1, then an inverse of A modulo M exists. Furthermore, this inverse is unique modulo M. So that is any other inverse is basically the same modulo M. Okay, so like in that example where 5 times 5, right? You guys realize 5 times 5 mod 6 is equal to 1, right? So we said that 5 bar, we said that the inverse of 5 is 5, yes? Yeah. But also you guys realize that 5 times 11 mod 6, what's the deal with that? 5 times 11 mod 6, what would that be? That would also be 1. And so would 5 times 17, okay? Mod 6. What's 5 times 17? Is 50, 85. Okay, is that right? So let's see, 5 times 17 is 85, but if I take that modulo 6, I am telling you, you will get 1. So it seems like 5, 11, and 17 are all different inverses of 5, but are they really different inverses of 5? No, they're really all the same as 5 mod 6, right? And notice that 5 mod 6 is equal to 11 mod 6, and this is also equal to 17 mod 6, etc. Okay? So this inverse is unique modulo M, which means any other inverse is basically the same in that modulus. Okay? So every other inverse of A modulo M satisfies it. Satisfies it. If you take it modulo M, you're just going to get A bar modulo M. Yeah. Okay. We're going to talk a lot about greatest common divisors. Turns out this is a very, very important topic. And it was talked about in the Heart of Mathematics, probably just lightly touched on. We're going to go a little bit deeper here. And we're going to go all the way back to Euclid. Okay. Euclid is the one that really started the discussion in any kind of depth on greatest common divisors. Okay. Any questions on this so far? So when does an inverse exist for A modulo M? If A is relatively prime to M, relatively prime, yeah? Turns out it's if and only if, yeah? An inverse for A will exist modulo M if and only if A and M are relatively prime, okay? That is, they have no common factors other than 1. All right, can we talk about greatest common divisors a little bit? And notice Euclid makes an appearance here, yes? Talk about the Euclidean algorithm. Actually, Euclid was the one that rigorously wrote down the definition of the division algorithm, okay? But we're going to talk about something called the Euclidean algorithm that helps us find divisors, or greatest common divisors. Okay? All right. Greatest common divisor. How about this? Before you read that, let me just ask you, how would you define greatest common divisor for two numbers? What does that mean? Greatest common divisor. I'm legitimately asking you, how would you define it? If someone walked up to you on the street and said, hey, I can't remember what greatest common divisor means, what would you tell them? Yes, Hannah. Yeah, it goes in evenly into both, right? So yeah, it's the greatest, so it's a divisor. Yeah. It's not just a divisor, it's a divisor that's common to both of them. So it goes into both of them. And it's the biggest one. Yeah. Right. So I mean, it's all right there in the terminology. It's a divisor, it happens to be common to both, and it is the biggest possible one you can come up with. Yeah. Okay. So here's kind of the way we mathematize what we just said. A and B are integers, not both 0. Okay. If one is 0, that's fine, actually. The largest integer D, such that D divides A and D divides B, is called the greatest common divisor of A and B. So it's a common divisor and it's the largest among those. The greatest common divisor of A and B is just denoted by GCD AB, like that. Okay. There's some other more confusing notation for it that I'm not going to get into. Well, I'll at least say this. There is a really confusing notation, and it's just like this. Okay, you actually put parentheses around A and B like that, but what could that easily be confused with? The ordered, like an ordered pair, right? Coordinates of a point in two-dimensional space. Silliness. I don't know why that's a prominent notation. I just want you to be warned about it. Okay, so are we clear on what the definition of greatest common divisor is? Okay, so is there a good way to actually find greatest common divisors? Well, that was a question that was on Euclid's mind, and he found a way. Okay, here it is. This is the so-called Euclidean algorithm. Okay, here's what we do. And it turns out that this is actually giving us the greatest common divisor, believe it or not. So I want to kind of show us how to do this by way of an example. I'm claiming that 35 has an inverse modulo 8. Okay, that there's something I can multiply 35 by, take it modulo 8 and get 1. Okay, so here's what Euclid did. He said, all right, 35 and 8. I am going to divide 35 by 8. How many times does 8 go into 35? 4. And what's the remainder? 3. So he did his famous division algorithm. He said 35 is 8 times 4 plus 3. And here's what he does next. He says, okay, I'm going to take these two numbers and those are going to form I'm going to divide 8 by 3 in the next line, right? So I'm going to divide 8 by 3 in the next line. How many times does 3 go into 8? 2. And the remainder is 2. So Euclid goes, all right, there's 3, there's 2. I'm going to divide those down in the next line. Yeah? Okay. 3 is equal to 2 times 1 plus 1. Yeah? And I mean, he could do the process again. He can take 2 and 1, go down the next line. So he always takes the divisor and the remainder. So you take the thing you divided by and the remainder, and that forms the basis for what you do at the next step. Okay? The GCD, and this will actually justify this in just a minute. The GCD of 35 and 8 will be the last non-zero remainder. What's the last non-zero remainder in this process? Notice that, you know, the numbers keep getting smaller as I kind of march through these steps, yes? And what's the last non-zero remainder here? What is it? 1. Okay. Turns out that the last non-zero remainder will actually be the greatest common divisor. Okay. Why? Why is that thing going to be the greatest common divisor? Well, we'll talk about that. But does this process kind of make sense? All he's doing is he starts with 35 and 8. He divides. He takes the dividend and the remainder, and he takes those down to the next line, and he keeps doing that over and over and over again. Okay, until he just ends up getting 0. Okay. Does this process make sense? Yeah? Okay. So watch. Oh, by the way, here's like a little computer program code way of doing this. Okay. This is what a computer scientist would call pseudo code. You basically just keep doing this thing where you constantly take the remainder and the dividend. Okay, or actually the divisor, you take the divisor and the remainder and you just go down to the next line and you kind of loop through that process over and over and over again. Once you take C++, you'll see that this kind of pseudo code plan for how you're doing something will become pretty typical. It'll help you write your program. So look, I want to talk through this example just to make sure we fully understand it. Look, this is exactly the same as what we just did, right? 35 and 8 is what we started with. Okay? We divide 35 by 8. That gives us a quotient of 4 and a remainder of 3. Yeah? Then we take 8 and 3 and we go down to the next line. Then we take 3 and 2 and go down to the next line, etc. Okay? Now this paragraph I wrote right here is really the explanation of everything that's going on. Okay, so let's just talk this through together. This is really my goal for the entire lecture, is for us to just understand these last couple of sentences right here. Okay? Any common divisor of 35 and 8 is also a common divisor of 8 and 3 because of the first equation. So that first sentence right there, if we can just understand that, I'm telling you we're going to be in good shape. Any common divisor of 35 and 8, because after all, think about it. 35 plus 8 times -4 is equal to, this thing says that 35 plus 8 times -4 is equal to what? 3, correct? So look, what if I had something that divided evenly into both 35 and 8? Well, if something divided evenly into both 35 and 8, wouldn't it divide this whole thing? Yeah? Because that's just a combination. Remember we said an integer combination of those two? If something divided evenly into 35 and 8, then it would divide evenly into that sum. But what's that sum equal to? 3, excuse me, yeah? So first of all, if something is a common divisor, that is, it divides both 35 and 8, then it will also divide 3, yeah? What if something divides 8 and 3? Well, look at the right-hand side of this. If something divides 8 and something divides 3, right? If something divides both of those things, then won't it divide this combination of those two as well? Yeah? If something is a common divisor for both 8 and 3, then it will be a divisor for 8 times 4 plus 3 also, yeah? That's just a combination of 8 and 3. And therefore, it will be a divisor of what? Look, 8 times 4 plus 3 is 35, yes? What I'm saying is, by kind of shifting stuff around in this first equation, we see that anything that is a common divisor of 35 and 8 is also a common divisor. I'm not saying greatest. Anything that is a common divisor of 35 and 8 is also a common divisor of 8 and 3. So anything that's a common divisor of 35 and 8 is also a common divisor of 8 and 3. Yes? Well, guess what? I can do that with the next line also. Okay, and here I say, if C divides 35 and 8, then C divides 35 minus 8 times 4, which is 3, which is by the first equation. Similarly, if C divides 8 and C divides 3, then C will divide 8 times 4 plus 3, which is 35 by the first equation. This is basically what we just talked through, yes? So I basically just kind of wrote out what's going on there, yeah? By the first equation, anything that is a common divisor of 35 and 8 is also a common divisor for 8 and 3, yes? So, I mean, hypothetically, if 5 was a common divisor of 35 and 8, which it clearly isn't, yes? If 5 was a common divisor for 35 and 8, then it would also have to be a common divisor of 8 and 3. And anything that is a common divisor of 8 and 3 would also have to be a common divisor of 35 and 8. I'm just repeating myself here, yeah? Thus, the first equation shows, since any common divisor of 35 and 8 is also a common divisor of 8 and 3 and vice versa, the set of common divisors for 35 and 8 is the same as the set of common divisors for 8 and 3, yes? So that is, by the first equation, the set of common divisors of 35 and 8 is the same as the set of common divisors of 8 and 3. Therefore, if I take the greatest of those, it's going to be the same, yeah? I mean, for crying out loud, it's the same set of common divisors. Therefore, the GCD of 35 and 8 is the same as the GCD of 8 and 3. And hey, what do you think I can do with the second equation? Same thing. I could say the GCD of 8 and 3 is going to be the same as the GCD, right? The GCD of 8 and 3 is the same as the GCD of 3 and 2, right? Just like I said, the GCD of 35 and 8 is the same as the GCD of 8 and 3. I can do the same thing with this one, yeah? Same set of common divisors for 8 and 3 is the same as the set of common divisors for 3 and 2, which means the GCDs are the same. And that little step down process, I see that the GCD of 35 and 8 is the same as the GCD of 8 and 3, is the same as the GCD of 3 and 2, which is the same as the GCD of 2 and 1, which is 1, okay? So that little division algorithm that kind of keeps repeating itself on the way down reduces the GCD problem to a simpler and simpler and simpler thing, okay? The Euclidean algorithm is very powerful, okay? And it's very quick. It's easy to program into a computer, and it finds GCDs very, very easily, okay? So any questions on that? Here, I just want to say, GCD of 35 and 8 is the same as the GCD of 8 and 3, and the GCD of the second equation says that the GCD of 8 and 3 is the same as the GCD of 3 and 2, okay? And the third equation says that the GCD of 3 and 2 is the same as the GCD of 2 and 1. And at that point, you're like, good grief, I can do that in my head, right? What is the greatest common divisor of 2 and 1? 1. Okay, so it's that simple. The Euclidean algorithm is very powerful. Okay. All right, once again, there's that little algorithm that is kind of a pseudocode version of it. You just continue to take the divisor and the remainder down to the next line, and it gets simpler and simpler and simpler. What about finding the GCD of 4, 14, and 662? Ah, it's 2. How would we get that? Well, you go 662 equals, how many? Okay, 62 equals 414 times what? How many times is 414 going to 662? 1. And what's the remainder? 200 and something. 200 and what? 248. Okay? And remember, what you do is you take the divisor and the remainder, and you go down the next line. The GCD of 662 and 414 is the same as the GCD of 414 and 248, right? By the same rationale we had before. Okay, so what about 414? 248, I don't even think that goes in twice, right? That goes in once. And holy smokes, what's that? 166. Okay, so what do I do next? Divisor, remainder, yeah? So you go 248. So once again, 662, 414, what I'm saying is here, GCD of 662 and 414 is the same as the GCD of 414 and what? 248, which is going to be the same as the GCD of 248 and 166. We could rationalize that just like we did before in the simpler case. Okay, so 248, that's 166 times 1 plus what? 82, yes. Okay? And so these two guys will have the same GCD. Okay? So this is equal to the GCD of 166 and 82. It's getting simpler, yeah? Okay, so 166 is equal to 82. Now we're in business. That's 82 times what? Plus 2. Oh man, now we're really in business. So this is the GCD of 82 and 2, and for crying out loud, the greatest common divisor can't ever be bigger than one of the two numbers. Do you know what I'm saying? What is the biggest number that goes into 2? 2. Therefore, the greatest common divisor is 2. And I'm telling you, if we went one more step, we would get a remainder of 0. You know what I mean? So you would go 82 is equal to 2 times what? 41 plus 0. Of course, the greatest common divisor of 2 and 0 is actually 2 also, yeah? I'm telling you, this is also the GCD of 2 and 0. What's the largest thing that divides? Everything divides evenly into 0, yeah? Okay, the greatest common divisor of that is also 2, okay? But 2 makes an appearance right here at the last minute before the end. And that is the GCD. The last non-zero remainder is the GCD of those two things. Yeah? Okay, we'll return to this on Wednesday, and we'll see how it helps us immensely in a number of ways.